Hey everyone, welcome back. This is the video series where I work through some network challenges using Elixir. If you don't know me, I'm Andrea and I'm a member of the Elixir programming language core team. If you want to follow the whole series, you can start from the first video, which is linked up here, or you can check out the whole playlist at the end of this video. Today's video is going to be about an interactive multi-client TCP-based chat server, as well as some testing best practices and some cool OTP tools. Okay, so let's get started. Okay, so today I wanted to start it with a little bit of cleanup, and I thought to do this offline and not in the screencast, but I figured someone might learn something from this, maybe. So let's go with that. The first thing I want to clean up is logs in tests. So right now, if I'm in our application that we're building and I run mixed test, the test passed, but I see a bunch of like useless logs over here. When I run mixed test, I want the output to be as clean as possible as a personal rule. Usually I do two things. I set the log level to warning or warn in tests so that info in the bugs log just don't show up, which would get rid of 5 out of 6 logs here as well. And the other thing I do is I capture warn and error logs and sometimes also assert on them because that can be useful. So for the first of the two, so setting the log level to warn, I will create a config directory and a config.exs file. So config.exs. Okay. And I will say import config. And I will say if the config is test, then I will config the logger application and the level will be warn. Okay. So I will usually you'd have a file for each mix environment, but I'm fine with just this for now. It's really simple and it does the job. So if I run mix test now, we can see that, as I said earlier, 5 of the 6 logs are gone. The debug and info logs are gone. The last one is this one that comes from the first thing that we did here. It was an echo server test, and it's this one. And you can tell because if I run this particular test over here, you can see, or I guess this particular one over here, current test. If I run this one, that's where the log comes from. So what I'm going to do is I'm just going to use tag capture log. So with this is a tag that XUnit understands, and it will just set up capture log for this particular test. I could use XUnit.capture log and kind of pass this whole thing if I wanted to assert on the log, but here I don't really care. So I'm fine with this. If I run tests again, the logs are clean, which is fantastic. All right. Another thing I will do is make all the tests asynchronous. Because there are no race conditions across test cases. We're starting all the servers on different ports, so we don't really have any overlap. So the easiest thing to do this, I'll just go through all of this and I'll say async true, and the prices server is also going to be async true, and this is going to be async true, and then there's a test case which is for the data structure, which is also async. Easy to do async, and it's not going to be much faster. You can see it takes 70 milliseconds in both cases, but before it was 70 milliseconds of sync time, now it's 70 milliseconds of async time. It's probably, because like these are too small to actually matter. The tests are not really doing a lot, so they're really fast anyways. But as we keep adding tests, this is hopefully going to matter. It's going to make the test suite faster in general. Okay, that's better. So now let's go over today's problem. So today's problem is about building a simple chat. This is really exciting. I'm very excited for this. We'll finally have different connections interact with each other, because until now we've always dealt with connections that would be kind of isolated. So this is going to be a fun challenge that will require a bit more thinking and also a bit more OTP. So it's going to be fun. I want to clarify one thing. In this series, I'm trying to avoid using external libraries when possible. We used a JSON library in one of the past videos, but that's just been about it. We didn't use anything else that doesn't ship with Elixir or Erlang. We could use several tools here to deal with TCP connections and pooling and broadcasting and more, but I'd like to stick with what ships with the standard library so that we learn the inner workings of these networking tools, as well as how usually you would use them to build the sort of libraries that then we commonly use in the Elixir and Erlang ecosystem. First up, the message format. Each message is terminated by a new line. Its message is on its own line. So that's great because in a previous video, which I'm going to link here, we already learned about the packet line option for GenTCP. So go watch the video if you want to learn more about it. I'm not going to go in depth into that option over here. But now on to the more exciting parts of the exchange protocol. So in order, what happens? You can go, the Protohackers problem is linked below, so you can go and read the description, in your own time. But I'm just gonna assume that you kind of read this, and I'm gonna summarize the problem, right? So the exchange protocol works sort of like this. First, a client connects to our server. Then the server sends a welcome message, which they are free to decide. Here it's welcome to Budget Chat, what shall I call you? And then third, the client sends a username, which the server has to validate. So the client responds with a username. Then the server must send a message to the new client listing all the connected clients in the room. Then the server must send all other connected clients a message saying that the new client joined. So this is all very natural, but that's how the protocol works. And when a client sends any message, the server must relay that message to all other clients, except for the client that sent it. And when a client disconnects, the server should send all other clients a message saying that the particular client left the chat. So this is kind of very, very basic chat, and it's all stuff that makes sense, I think. But that's the protocol, and it's good to have it kind of written down. Great. So it sounds like a lot, but it's going to be easier to implement in practice, I think. So we have everything we need to get started. Let's kick things off by designing our architecture. Our problem requires some shared state one way or another. We need it for a few reasons. First of all, we need to know all the connected clients at any given time. And we also need to do frequent broadcasts where an action from a particular client causes us to send a message to all other clients. Because of this point, we'll need a data structure that holds for each client the username and the socket that holds the connection. These two pieces of information should be enough. The kinds of operations we'll do on this state are retrieve the username associated with a connection or a socket, and we'll need these to broadcast messages with the right username. Then we will get all the currently connected users and their respective sockets, which we'll need for broadcasting. And last, we will need to be able to delete a username socket pair when a user disconnects. I find that knowing what operations to do on a data structure can help a lot with choosing the right data structure. So now that we know this, let's go over a few options. Okay, so we have a few built-in options for shared state in Erlang and Elixir, and choosing the right one can depend on many factors, but in this case, let's focus just on two possible solutions. The first one is agent, the agent module, and the second one is ETS tables. And these two solutions sort of represent two possible ways we can go about this. So an agent is a process that holds state and that other processes can interact with to retrieve and manipulate that state. It provides perfect consistency at the cost of being slow, usually. So because the way it works is that an agent process handles requests sequentially. So we can only retrieve or modify the state one request at a time. There's no concurrency, right? So this is likely fine for our use case in this particular problem, but it can be problematic for many, many other use cases. The other alternative we can explore is ETS tables. An ETS table is essentially an in-memory key value store shared across processes, across all processes running on the beam. It's fast and it's quite scalable, but it doesn't really support arbitrary atomic operations like agents do. It only supports the set that's provided by ETS itself. It would probably work in our case though, because the operations I mentioned earlier are either on a particular key, which is the socket, or on all keys, which is for broadcasting in general. We don't expect a lot of traffic here, but I still probably go with an ETS table since it's I find it kind of a better practice in a case like this, because I wouldn't want a bottleneck, and a single agent holding the whole state could probably eventually turn up into a bottleneck. The complexity of using an ETS table here is not much more. And again, we can do all the operations we need with the ETS table. So in this case, I'll just go with the ETS table. So we will need a process to be responsible for the life cycle of the ETS table. That's how it works. An ETS table always has an owner process. Luckily, our server's life is tied to the main gen server. We have a main gen server that accepts connections. And if that server is alive, it means that the server if that process is alive, it means that the server is alive. So we can make that process the owner of the ETS table, and we should be fine. So what I will start with, I'll start by copying the JSON server from a couple of videos ago to have a skeleton process. And that's going to be in Protohackers here. And I will copy it to Protohackers budget chat server. Okay, let's open this one. I will rename the server to budget chat server. I will copy this to our application to start it as another child. And then I will change the port to be 5004. I believe we are at 5004 at this point. If I do run no halt, we should, yes, okay. And I will call it starting budget chat server. Great. The reason I copied the JSON server from a couple of videos ago is just so that we have the line-based protocol already sort of ready to go. Okay, the first thing we'll do is we'll add an ETS field to the def struct here for the gen server state. I will close the terminal because we will want to keep a reference to the ETS table in our server. ETS tables can be named or not named, and we can refer to them by name or by their identifier that's returned by calling ETS new. In this case, I could use a name table because we effectively only have this budget chat server running in our application, but we don't really need to. We can pass around the reference to the ETS table to the children, and doing that allows me to start multiple budget chat servers if I wanted to, for example, for tests. We're not really going to do this now, and it wouldn't really work right away because they'd be binding on the same port. But I think it's a good practice to not make global resources when it's not necessary. So I'm just not going to make a name table here. So we can start the ETS table and store it in the state when we initialize our server. So here we start our supervisor, and then the next thing for tasks, and then the next thing I'm going to do is I'm going to start the ETS table or create the ETS table. It still needs an ID. I'm going to go with the module for now. It's fine, even if it's not going to make it unique, but at least I can change this very easily later on if I wanted to. And oh, something strange happened. And the other thing I'm going to do is I'm going to pass the public option, and this option allows every process actually to read and write to the table, which is what we want, so that both the server process as well as all the connection processes can write and read to this ETS table, which is one of the reasons why this scales. And then I'm going to just store this in the state when I'm constructing the state here. Fantastic. Cool. Next thing, we're going to get rid of this echo lines until close function. We're just going to write a new one because there's a lot of stuff here that we don't really need. And we are going to clean this up as well. So let's start fresh from handle connection. What are we going to do? As the interaction protocol described, the first thing we'll do is have the server ask the new client for its username. We're adding a new line ourselves. So what we're going to do, gentcp.send, and we'll pass the socket and then say, what's your username? Question mark, new line. Fantastic. I will also match on OK. I usually wouldn't do just a straight up match like this because it would have failed with a pretty hard to debug error, not very friendly error, which would be just a match error saying this match failed on line 54 here. But at least if the sending fails, the process controlling this connection will just crash, and the main while the main acceptor gen server, the main server stays alive. So for now, I'm okay with this. It's just a way to make sure that the server is actually the socket is actually open for sending. The next step is waiting for the answer and validating it. So what I'm going to do is I'm going to call gen_tcp, our old friend, gen_tcp.receive socket, whatever data, and I'll give the user kind of like 300,000 milliseconds, which would be 60 seconds times 5 minutes times 1,000 for the milliseconds as the timeout. If I get a line during this time, then what I will do is I will actually do the validation, right? So the first thing is I trim the line of white space, and then I say if the username matches this regex. I usually wouldn't use a regex. I'm not a fan of regexes at all. I'd rather build like a hand roll parser for something, because usually it takes away a lot of headaches for me. But in this case, it's such a simple regex and it's such a simple case that this kind of like makes it maybe a good use case for regex. So the problem description said that this needs to be a alphanumeric character only. Alphanumeric characters only is what I mean. And I will do this. So if a username matches, just a string made of one or more alphanumeric characters, then for now we'll just logger debug and say username connected. Okay. So one thing is that, as you may know, these two characters match the end and the start and the end of a line. So it can be problematic if you have multi-line input, because it might not match. In this case, we're fine because gen_tcp is never going to return more than one line if we're using the packet line option. So this is always going to be a line, and we're trimming it. So this is going to work for our use case, but just good to know. Okay, in this case, we'll just kind of shut down the connection to debug so we can use it for testing in a second. If the username is invalid, what we're going to do is we're going to send a message saying invalid username and the new line, and we're going to shut down the socket and kind of kick out the client. If there's an error here, for now we'll just return okay. It means the client kind of never really got to tell the username, never really got to connect, so we'll just not do anything. So perfect. Also, we want to probably close the socket here in case it's still open, in case it's a timeout, for example. Perfect. Let's we have a rudimentary setup. Let's just try it out. So it's starting. Fantastic. Let's open up another terminal, and we'll use a tool that we haven't used yet, which is Telnet, which is kind of a CLI utility to send and receive network data. It's very, very, very old. It's in all systems. It's just nice for these kinds of cases. We'll see it in action. So if I connect to localhost 5004 and I say, what's your username? I'm going to say Andrea. And this one says, okay, username Andrea connected, right? And this is good. And if so the debug log is there. If I exit this and I try with an invalid username, for example, hello world with a space and a exclamation mark here, it says invalid username and it kicks me out. So cool. Let's move on to telling us which clients are connected. Okay, so we want the server to send a message to newly connected clients telling them what are the users in the room. Let's start with a very, very basic message. For now, we will not even check the clients. We will just say that if a username connects correctly, we will say gen_tcp.send socket, and we will say the room contains, and for now we will not do anything. So now we actually have to figure out who's in the room. And how do we do that? Well, through our ETS table. So what we're going to do is we're going to insert each new user in the ETS tables first, as soon as they connect and the username is validated. To do that, we'll have to pass down the handle to the ETS table to every spawned task. So we'll start by doing that. So here, instead of saying handle connection just socket, we'll also say state.ets. Okay. And there's my face on it, but there you go. Handle connections socket state.ets, and here this is going to take the handle to the ETS table. Before sending the message, what we're going to do is we're going to use ets.insert, which is the function to insert the data in the ETS table. We're going to pass the handle to the ETS table, and the object that we're going to insert is a tuple made of socket username. By convention, the first element of a tuple that you insert in the ETS table is the key. So, and in our case, that's fine because we're going to do operations keying by socket. So it should work fine for now. You can also pass options to tell which is the key, but in our case, this works just fine. Perfect. After we've done that, we can essentially query the whole table for all the keys to send all the connected users to the client. So the ETS, we're going to use a function called ETS match. So we're going to say all users equals ETS.match. We'll pass the handle, and then we're going to have this strange thing here, which I'll explain in a second. So this is a match specification. The second argument here is a match specification. That's how Erlang calls it, at least. And it's used to match on tuples in the table and return selected elements. So match specifications are powerful, complex, and they're kind of awkward to write. So we won't really go into too much detail, but suffice to say that in this case, I'm saying that I really don't care about the first element here. I care about the second element of the tuple. I care about the usernames that are connected, not about all their sockets. So I want to return just the second element of each tuple. There's no condition. I could filter elements here, which I'm not doing. So it's just, there's a bunch more stuff that I could do, but in this case, I really don't need to. Great. And what I will do, so these are all the users. And what I will do is I will use them for joining them. So I will say here, enum.join all users, and I will join them with a comma. So now I'm retrieving all the users, then I'm inserting these users, so it's not in that list, and then I'm sending that user a message saying that all the users are these. So let's try this out again. Let's restart our server, and let's try this out again with our telnet sessions. So I'll say, what's username? Andrea. Great, let's split up another terminal and say telnet again. What's your username? Say Jose. Okay, and it says the room contains Andrea. Perfect. If I were to split up and go for another one, say, what's your username? Maybe Eric. And the room contains Jose and Andrea. Perfect. So this seems to be working. I'll shut some of this down. Perfect. Let's move on. All right, now on to broadcasting that a user connected. To do that, when a user connects, we have to send a message to all other users. To avoid having to filter out our new users, we will send the message before inserting the user into the ETS table. So kind of like we did over here, where we query the ETS table first. Since when a user connects, we'll need the other connected sockets as well, not just the usernames. We'll change our call to ETS match here to actually match on return everything. So we're gonna say just return the whole tuple. And this way we just get the sockets and the usernames just with one call. And what we're going to do, we need to change this is not going to work anymore. So we'll say usernames, we'll change that. Essentially, we're going to say enum.map join. All users will join still with a comma, but in this case, we'll go over socket username tuples and return the username. This is a list of one element because that's how ETS match works. I will not go into detail, but that's just how it looks like. And now instead of saying enum join here, I'm just going to say usernames. Perfect. Then I will insert the username. And now I have all the sockets available. So it's now time to broadcast to all the connected users. And I will do that by doing this enum.each all users. Again, I will have the socket and I will not care about the username in this case. And what I will do here, chant tcp.send socket, and the message will be something like username has entered the chat. So the username being the user that just connected. And I'm broadcasting these to everyone else. A very fascinating thing about this, in my opinion, is that is this call to gentcp.send. Because if you think about it, can you notice what's interesting about it? For me, it's the fact that we're sending a message to a TCP socket from a process that doesn't own the socket, right? So that's possible and optimal in this case, because we're not having to bottleneck messages through a single process, right? But it's interesting because we cannot do that for receiving. So each TCP socket in Erlang and Elixir has one controlling process, which is a process that owns that socket. And that's the only process that can receive messages and data from that socket. Sending, however, is kind of public, so everybody can send to a socket as long as they have access to that socket. So, and that's perfect for us because we can broadcast to all the other connected clients without having to tell them that we're broadcasting to them. We're just sending data directly to their sockets from the server here. Cool. So let's test this out. I'm going to try this out over here. Again, telnet, what's your username? It's Andrea, and says the room contains no one. And then I telnet again, what's your username? Jose. The room contains Andrea, and now it says Jose has entered the chat here. So we got the message broadcasted to everyone else. If I split another one of these, and again I do what's your username, Eric, it broadcasts Eric has entered the chat to everyone. You can see a very obvious mistake I made, which is forgot the new line in a bunch of places, over here and over here. So that's my bad. Okay, so but this is working correctly. So only two things left in the interaction protocol now: chat messages and user has left messages. Chat messages are pretty straightforward. The first thing we'll need to do is keep each connection alive, because right now you're kind of connecting to the socket here, then you're sending the message, and then we're not really doing anything else. So we'll create a new handle chat session or something like this, a function that will recurse until the connection is closed and will just listen for messages. So we'll call this over here, handle chat session, and we'll pass the socket, the ETS, the handle to the ETS table, and the username. Just we could retrieve the username by querying every time the ETS table with the socket as a key, but we have it, so why not send it? Why not pass it down? And we'll define this as handle chat session socket ETS username. And what we're going to do in here is we're going to just listen for messages from this user. So gentcp.receive, again, the socket, again, 0 for all the available bytes. And again, a timeout of 5 minutes should be fine. If you're inactive for 5 minutes, you get kicked out, essentially. That should be fine. If this returns OK message, we will trim the message so that it doesn't have the new line and it doesn't have any unnecessary white space at the start and at the end. And once again, if the message is not empty, and this is kind of an optimization because otherwise someone could just press enter, 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 and we will just get infinite messages and broadcast empty messages to everyone. So let's just skip that. So if the message is not empty, then we would say we need to get again all the sockets by doing the same thing we did here initially above, which is just use this match spec syntax. We don't really need the usernames now, so we're actually only going to get the sockets in this case. And I'll use this match thing, and then I'm going to use a for comprehension to broadcast the message to all other sockets. So I'm going to say for other socket in all sockets. I want to have a filter in my comprehension saying that the other socket should be different than sockets so that I don't send this message to the users that just sent it, that just typed it. I'm going to do gen tcp.send other socket. And the message is going to be something like username and then the message that they sent, message, and this time a new line, which I will remember. I misspelled this, all sockets. Fantastic. You might notice here that I'm not matching on OK here, like this. And I'm doing that because I'm not sending to the socket that this process owns. So if there's an error in sending to another socket, I don't want to care much in this process. I just want to kind of fire and forget. Like if that process's socket is closed or there's been an error, this process will just not care. It will try to send it, but it will not crash, because otherwise, if there's a client that disconnects abruptly, then it could cause all other clients to disconnect if they have because they would have errors as soon as they type, because they would have errors trying to send a message to that socket. It's about race conditions really, but in this case, we're fine with the kind of resiliency strategy of saying if you can't deliver a message to another user, it's fine. So should be okay. And after doing this, for now, if everything has gone well, we've broadcasted the message, and then we'll call this recursively. So we'll say handle chat session socket ets username. Fantastic. And then we have leave messages. So leave messages is when a user leaves. So when can that happen? Well, it can happen, usually we notice by noticing that there's an error in our GenTCP receive. So we don't really care about the reason, but for any error we get, we'll do the same thing here that we did before. So we'll say get all the sockets. I'll just copy paste this, and then I'm gonna say the exact same thing here. So for other socket, if it's different than socket, then I send a message. It's just a message that's different, and this time it's gonna be username has or left, just username left. That should be fine. What's wrong here? Other socket, all sockets, sorry, misspelled again. And so I'm gonna broadcast this message to all other sockets. Then what I'm gonna do is I'm gonna do gentcp.close the socket. I don't really care about the result because it's probably closed already if I got an error here, but I'm gonna just super make sure that it's closed. And then importantly, I'm going to delete the ETS, the socket from the ETS table. As you can see, delete takes a key this time, doesn't take a tuple or a selector. You have ways to delete with match specs, but in this case, we can just pass the key, which is the socket, and it's gonna delete the tuple that identifies that key value pair. So let's try this out. I will again restart the server. Great, and I will again do, what's your username here, Andrea. Again, what's your username, Jose. And again, what's your username, let's say Eric. So Eric has entered the chat. Andrea, the room contains Andrea, the room contains Jose Andrea. Hey friends. So Andrea wrote hey friends to everyone. Jose can reply hello. And he shows up. Eric can reply hey. And he shows up. Now if Eric leaves, we get Eric left here. If, for example, Jose leaves, we're gonna get Jose left. So it seems like everything is working. One thing that I do wanna bring up, which I think is really important, is this ETS delete. Can you figure out what's the potential problem with this? So the potential problem with this is that if our task that's handling this connection crashes for any reason, it could be any reason. We're not really writing code that's supposed to crash. Like this is not supposed to crash, but it could. We could have a runtime error. We could have, a mistake somewhere. Username might not be something that you can turn into a string here for some reason, and it could have a protocol error or something. Like we could have any runtime error here that could cause the process to crash. It would be a bug that we introduce, but usually in Erlang and Elixir, it's totally fine because, okay, that process would die. It would not affect the server. It would just shut down the socket because it's connected to the process, and that would be the end of it. The problem here is that we have a shared resource, which is this ETS table. And what happens is that if an error happens in this function, we will not ever reach this ETS delete call, and we will not delete the entry from the table, which is a potential memory leak. So if we would have an error that would happen over time, clients would keep connecting, and maybe this error would keep happening, and we would never clean up the table, and the table would just keep growing indefinitely. We would never delete anything from the table. So usually in this case, I'm just going to leave it at this. I'm just going to tell you and leave it at this because it's a bit more complex to handle that. What I would do, just to tell you sort of the high level picture of what I would do to fix that, is that we would probably have a different process whose we could go about it in a couple of ways. One of them would be to have a different process that monitors all the tasks that get spawned. So a task gets spawned and then kind of registers itself with that process. And this process would just monitor these tasks. And if a task crashes, it would clean up its socket from its socket and username tuple from the ETS table. So that would be an option. Another option would be, and that also has some things to consider. So what if that process crashes and so on and so on, but that's kind of a way to get started. And another option is to periodically go through this ETS table and purge it. So essentially, periodically go through the ETS table and check if all the sockets that are in there are effectively open sockets. And if they aren't, then we can delete them. So if their process is alive, yada yada. So these are kind of the options that I would go for. There are like unnecessary complexity for this sort of problem. I think this is gonna solve, like it's gonna work with our challenge, but I think it's good to know, and I think it's a great thing to just keep in mind, because these are the sort of things that are kind of like a little bit more advanced, but when you're writing production application, you're gonna have to think through. Okay, last but not least, let's test this whole flow out with some automated tests. We didn't really write automated tests for this yet because I wanted to focus on the protocol, but let's do that now. I'm gonna create a file, Protohackers, in the Protohackers directory, budget chat server test. Great, and what I'm gonna do here, I'm gonna create the module, which is protohackers.budget chat server test. I'm gonna do useXunit.case async true. Okay, and what I'm gonna do here, I'm gonna cheat and I'm just gonna copy paste this from my notes. We're gonna step through this, but at least you will not have to look at me type all this stuff. But the whole flow is gonna consist of starting a couple of sockets, connecting them to our server. And then we kind of test the interaction. So for example, we say, okay, the first socket, we receive a message on that socket, and that message should be, what's your username? And then we're gonna send back sock1, great. And then this is gonna say the room contains nobody, perfect. Then we do the same on the second socket. We're gonna say, okay, what's your username? And then we say sock2, okay, the room contains sock1. And then we have a message on socket 1 that says sock2 has entered the room. Then we send some messages, we tested they're broadcasted correctly. We close one of the sockets to make sure that we broadcast the sock2 left message. And then we open another socket and we check that the room contains only the socket. So we check that we kind of remove the socket that is connected, that we remove it from our ETS table and from our shared state. If I run mix test, oh, I used the wrong here. There you go. My bad. I was in the moment and I didn't really look at my notes too much. Okay, so tests pass. Great. So we will not, there's a bunch of more stuff that we could, this is kind of an end-to-end single test. There's a bunch more stuff that we would probably want to test, like, network issues and all sort of other things that could happen. But for now, I think we're good with this. And I think we're also ready to deploy this. So I'm going to just write fly deploy. Actually, first I need to go into fly toml here in the configuration. And I have to open port 5004. So I'm going to do that. 5004. Great. And I'm going to just run fly deploy. And I will see you in a bit when this finishes deploying. Great. Finish deploying. We can test. Let's remember the IP first here. Okay, it's this one. We can test this out locally by saying using telnet again. And I say, what's your username? Andrea. And then in another tab, I can just close a couple of these. Yep, I terminated it and say telnet, oops, telnet with this IP again. Perfect. The username is there. The room contains Andrea. Hello. So it seems like it's working just fine. When deployed as well. So let's move over to Protohackers and test the challenge. Okay, we're here. Let's paste in our IP and let's type out our port number and let's say check. Let's see how this goes. Cool, a bunch of stuff connected, pass. Okay, so we ran the test. Everything passes. So we can see that Protohackers tried to do a bunch of tests, tried to connect different users, connect users with the same name at some point, connect users with new names, then disconnect them, then just check that all the messages in the exchange protocol are correct. But it passes and we're good. Okay, done. I really love this problem because it shows a lot of things that are built into the Beam, like ETS tables and all the socket stuff. At the same time, it also shows that building something like a live interactive chat is not that hard after all, with all the basics, just the basics of TCP, right? Sending and receiving messages and closing and opening sockets, basically. At some point in the next videos, we will stop using active false or passive mode, as we can call it, and we'll move to message-based TCP, which feels more natural in Erlang and Elixir. I wanted to get this particular video done with the tools that we have learned in the previous videos and that we have explored in the previous videos, because there was a lot of, I think there was a lot to learn anyways in this video. But so from one of the next videos, we will start using active mode, which is going to be fun, I think. If you have any feedback or questions, leave a comment below, or feel free to reach out on Twitter or Mastodon. I would love to chat. Otherwise, I will see you on the next one.